In point estimation, the value of an unknown parameter is estimated by using an estimate or a point. In case of interval estimation, the value of two statistics is computed on the basis of the random sample of observations, and we put forward an interval based on these two statistics with the hope that this interval will include the true value of the parameter with some pre-assigned probability. In the present lecture, first we shall discuss how one can find a confidence interval by using a pivotal quantity. Some examples are discussed in this connection, and we discuss the method of obtaining a shortest length confidence interval or a shortest expected length confidence interval based on the pivot. So far, we have discussed the point estimation of a parameter, or more precisely, point estimation of several real-valued parametric functions. Such point estimates are quite useful, yet they leave something to be desired. In case of continuous distributions, the probability that the point estimator actually equaled the value of the parameter being estimated is 0. Hence, it seems desirable that a point estimate should be accompanied by some measure of the possible error of estimate. For instance, a point estimate must be accompanied by some interval about the point estimate together with some measure of assurance that the true value of the parameter lies within the interval. Instead of making the inference of estimating the true value of the parameter to be a point, we might make the inference that the true value of the parameter is contained in some interval. This is called the problem of interval estimation. Let x1, x2 up to xn be a random sample from a population with PMF or PDF f theta x, where theta belongs to script theta, which is a subset of the real line, is the unknown parameter. Let capital T1 and T2 be two statistics satisfying T1 less than equals to T2, for which probability under theta T1 less than equals to theta less than equals to T2 is equals to 1 minus alpha, where alpha belongs to 0, 1 open interval, does not depend on theta for all theta. Thus, the interval T1, T2 will include the parameter theta with probability 1 minus alpha. This means that if a large number of random samples of same size be taken and the intervals as mentioned above be determined on the basis of this sample, the 100 into 1 minus alpha percent of these intervals will include the true value of the parameter theta. The random interval T1, T2 is called a 100 into 1 minus alpha percent confidence interval for theta. The quantity 1 minus alpha is called the confidence level, and T1 and T2 are called the lower and upper confidence limits, respectively, for theta. Let us consider an example. Let x1, x2, xn be a random sample of size n drawn from normal population with mean mu and variance 1. Now we know that x bar, which is the sample mean, follows normal mu comma 1 by n. Therefore, probability under mu tau alpha by 2 less than equals to root n into x bar minus mu less than equals to tau alpha by 2 is equals to 1 minus alpha for all mu, where tau alpha by 2 represents the upper 100 into alpha by 2% points of the normal 0-1 distribution. Hence, by interchanging sides, we get probability under mu x bar minus tau alpha by 2 divided by root n less than equals to mu less than equals to x bar plus tau alpha by 2 divided by root n is equals to 1 minus alpha for all mu. Hence, x bar minus tau alpha by 2 divided by root n x bar plus tau alpha by 2 divided by root n is a 100 into 1 minus alpha % confidence interval of theta. Here it is to be noted that small x bar denotes the observed value of capital X bar obtained from the sample. Now we discuss a method of determining a confidence interval by using a pivotal quantity. First, we discuss what is called a pivot. Let x1, x2, xn be a random sample from a population with PMF or PDF f theta x. Here, the whole sample is represented by a vector x. Let q x comma theta be a real valued function of x, and theta q is called a pivot if its distribution is completely known under theta belongs to script theta. That is, q has a distribution that does not depend on the unknown parameter theta. Since the distribution of q is independent of theta, we can find two numbers, small q1 and small q2, such that small q1 less than q2. Probability under theta q1 less than equals to capital Q x comma theta less than equals to q2 is greater than equals to 1 minus alpha for all theta belongs to script theta. It is equivalent to probability under theta t1x less than equals to theta less than equals to t2x is greater than equals to 1 minus alpha for all theta. Hence, t1x comma t2x is a confidence interval for theta at confidence level 1 minus alpha. Now we discuss the concept of shortest confidence interval based on a pivot. For any fixed 1 minus alpha, there are many possible pairs of numbers q1 and q2. Probability under theta small q1 less than capital Q less than q2 is equals to or greater than equals to 1 minus alpha. Different pairs of q1 and q2 will produce different t1 and t2. We should want to select the pair of q1 and q2 that will make t1 and t2 close together in some sense. For instance, if t2x minus t1x, which is the length of the confidence interval, is not random, then we might select that pair of q1 and q2 that makes the length of the interval smallest. Or if the length of the confidence interval is random, then we might select that pair q1 and q2 that makes the average length or the expected length of the interval smallest. Thus, a shortest length confidence interval is the confidence interval for which T2x minus T1x is minimized and a shortest expected length confidence interval, which is abbreviated as SELCI, is the confidence interval for which expectation under theta T2x minus T1x is minimized for all theta belongs to script theta. To clear the concept, let us discuss some examples. In our first example, we consider a random sample x1, x2, xn of size n from normal mu, 1 population. To find the shortest length confidence interval for mu, we use the pivot q x, mu is equals to root n x bar minus mu, and we know that root n x bar minus mu follows normal 0, 1 for any mu. Hence, it is possible to find small q1 and small q2 such that probability under mu small q1 less than equals to root n into x bar minus mu less than equals to small q2 is equals to 1 minus alpha. After some algebraic manipulations, we get probability under mu capital X bar minus small q1 by root n less than equals to mu less than equals to capital X bar plus small q2 by root n is equals to 1 minus alpha. Therefore, T1x is equals to x bar minus small q1 by root n and T2x is equals to x bar plus q2 by root n. Hence, the length of the interval is given by T2x minus T1x, which is equals to q2 minus q1 into 1 by root n. It is not a random variable. So, our objective is to minimize q2 minus q1 subject to the condition probability under q1, probability under mu, q1 less than equals to capital Z less than equals to q2 is equals to 1 minus alpha, where Z is a standard normal variable. Let us define a function psi of q1 and q2, which is equals to q2 minus q1 plus lambda times capital F Z q2 minus capital F Z q1 minus 1 minus alpha. Here lambda denotes the Lagrangian multiplier and capital Fz denotes the CDF of capital Z. Hence, by differentiating psi with respect to q1 and q2, we get the following set of equations, and solving for 0 gives us the shortest length confidence interval. Note that the partial derivative of psi with respect to q1 is equals to 0 implies minus 1 minus lambda into small fz q1 is equals to 0. Here small fz represents the PDF of z. Also, the derivative of psi with respect to q2 is equals to 0 implies 1 plus lambda into small fz q2 equals to 0. From these two equations, we get small fz q1 is equals to small fz q2. By symmetry of the normal distribution, we get small q2 is equals to minus of small q1, and hence small q2 is equals to tau alpha by 2, where tau alpha by 2 denotes the upper 100 into alpha by 2% point of normal 0-1 distribution. Hence, the shortest length confidence interval for mu is given by the interval x bar minus tau alpha by 2 divided by root n, comma x bar plus tau alpha by 2 divided by root n. Here x bar denotes the observed value of capital X bar obtained from the random sample. We consider our second example. let x1, x2, xn be a random sample of size n from normal mu, sigma square population, where mu and sigma are both unknown. To find shortest length confidence interval for mu, here we use the pivot capital Q x, mu is equals to root n into x bar minus mu whole divided by s, where s denotes the sample standard deviation, which is equals to root over 1 by n minus 1 summation over I from 1 to n xi minus x bar whole square. Now we know that capital Q follows student t distribution with n minus 1 degrees of freedom for any mu, sigma. So it is possible to find two quantities small q1 and small q2 such that probability under mu, sigma small q1 less than equals to root n x bar minus mu divided by s less than equals to small q2 is equals to 1 minus alpha. After some algebraic manipulations, we get probability under mu sigma x bar minus q1 into s divided by root n less than equals to mu less than equals to x bar plus q2 into s divided by root n is equals to 1 minus alpha. Therefore, t1x equals to x bar minus q1 into s by root n and t2x equals to x bar plus q2 into s by root n. Hence, the length of the interval is given by t2x minus t1x, which is equals to q2 minus q1 into s by root n. Since s is a random variable, the length is also a random variable. Here actually we minimize the expected length of the interval, which is actually a function of q2 minus q1, and it is independent of mu. So our objective is to minimize q2 minus q1 subject to probability under mu sigma q1 less than equals to tn minus 1 less than equals to q2 is equals to 1 minus alpha. Here, as in the previous case, we define the Lagrangian function as follows. Psi q1 q2 is equals to q2 minus q1 plus lambda times capital F q2 minus capital F q1 minus 1 minus alpha. Here capital F represents the CDF of Tn minus 1 distribution. Hence, by differentiating psi with respect to q1 and q2, we get the following set of equations, and solving for 0 gives us the shortest length confidence interval. Here, the partial derivative of psi with respect to q1 is equals to 0 implies minus 1 minus lambda into f small f q1 is equals to 0. Here small f tn minus 1 represents the PDF of tn minus 1 distribution, and the partial derivative of psi with respect to q2 is equals to 0. 1 it implies 1 plus lambda small f tn minus 1 q2 is equals to 0. From the two equations we get f q1 equals to f q2. By the symmetry of the t distribution about 0, we get q2 equals to minus q1, and hence q2 equals to t alpha by 2 n minus 1, where t alpha by 2 n minus 1 represents the upper 100 into alpha by 2% point of a t distribution with n minus 1 degrees of freedom, and hence the shortest length confidence interval for mu is given by x bar minus t alpha by 2 n minus 1 into s by root n, x bar plus t alpha by 2 n minus 1 s by root n. Here x bar denotes the observed value of the sample mean and s denotes the observed value of the standard deviation. We consider our fourth example, our let x1, x2, xn be a random sample of size n from normal mu comma sigma square population. Suppose we want to find shortest length confidence interval for sigma square. Since mu and sigma square are both unknown, here we use the pivot capital Q equals to summation over I from 1 to n xi minus x bar whole square divided by sigma square. And we know that capital Q follows chi square n minus 1 for any mu comma sigma square. So it is possible to find two quantities small q1 and small q2 such that probability under mu sigma small q1 less than equals to summation over I from 1 to n xi minus x bar whole square by sigma square less than equals to q2 is equals to 1 minus alpha. After some algebraic manipulations we get probability under mu sigma summation I from 1 to n xi minus x bar square by q2 less than equals to sigma squared less than equals to summation I from 1 to n xi minus x bar whole square by q1 is equals to 1 minus alpha. And hence t2x minus t1x is equals to summation over I from 1 to n xi minus x bar whole square into 1 by q1 minus 1 by q2, which is again a random variable. So here we also minimize the expected length of the confidence interval, which is actually a function of 1 by q1 minus 1 by q2. Therefore, we have to minimize 1 by q1 minus 1 by q2 subject to probability q1 less than equals to chi square n minus 1 less than equals to q2 is equals to 1 minus alpha. As in the previous case, here we define the function psi, which is equals to 1 by q1 minus 1 by q2 plus lambda times capital F q2 minus capital F q1 minus 1 minus alpha. Here capital F represents the CDF of a chi-square distribution with n minus 1 degrees of freedom. Hence, by differentiating psi with respect to q1 and q2, we get the following set of equations, and solving for 0 gives us the shortest length confidence interval. The partial derivative of psi with respect to q1 is equals to 0 implies minus 1 by q1 square minus lambda into small f q1 is equals to 0, where small f chi square n minus 1 q1 represents the PDF of the chi-square distribution with n minus 1 degrees of freedom. And the partial derivative of psi with respect to q2 is equals to 0 implies 1 by q2 square plus lambda small f q2 equals to 0. Solving the two equations simultaneously, we get small q1 square into small f q1 is equals to small q2 square into small f q2, which is equals to e to the power minus q1 by 2 into q1 to the power n plus 1 by 2 is equals to e to the power minus q2 by 2 q2 to the power n plus 1 by 2. From this equation we can solve q1 and q2. We consider our next example. Let x1, x2, xn be a random sample of size n drawn from rectangular 0 theta population. We want to find shortest length confidence interval for theta. Here we use the pivot capital Q x ordered n comma theta, which is equals to x ordered n divided by theta. Here x ordered n denotes the maximum of x1, x2, xn. We know that the PDF of w, which is equals to x ordered n, is given by pw is equals to n by theta to the power n, w to the power n minus 1, w lies between 0 to theta. If we consider the transformation y equals to w by theta, then the PDF of y becomes py equals to n into y to the power n minus 1. Y lies between 0 and 1 and it is independent of theta. Therefore, it is possible to find two quantities small q1 and small q2 such that probability q1 less than y less than q2 is equals to 1 minus alpha. which is equivalent to probability under theta q1 less than x ordered n by theta less than q2 is equals to 1 minus alpha. And therefore probability 1 by q2 less than theta by x ordered n less than 1 by q1 is equals to 1 minus alpha. And finally we get probability x ordered n by q2 less than theta less than x ordered n by q1 is equals to 1 minus alpha. Therefore T1x equals to x ordered n by q2 and T2x equals to x ordered n by q1. And therefore the length of the interval is given by T2x minus T1x is equals to x ordered n into 1 by q1 minus 1 by q2. As in the previous case, here we again minimize 1 by q1 minus 1 by q2 subject to the constraint integral over q1 to q2 n into y to the power n minus 1 dy, which is equals to q2 to the power n minus q1 to the power n is equals to 1 minus alpha. Now 1 minus alpha whole to the power 1 by n less than q2 less than equals to 1. Differentiating the length, which is equals to 1 by q1 minus 1 by q2, which is denoted by L with respect to q2, we get dl by dq2 is equals to minus 1 by q1 square dq1 by dq2 plus 1 by q2 square. Again q2 to the power n minus q1 to the power n is equals to 1 minus alpha implies n into q2 to the power n minus 1 minus n into q1 to the power n minus 1 into dq1 by dq2 is equals to 0, and therefore dq1 by dq2 is equals to q2 to the power n minus 1 by q1 to the power n minus 1. Thus we get dl by dq2 is equals to minus 1 by q1 square into q2 to the power n minus 1 by q1 to the power n minus 1 plus 1 by q2 square, which is equals to q1 to the power n plus 1 minus q2 to the power n plus 1 whole divided by q2 square into q1 to the power n plus 1, which is less than 0, and hence L is a decreasing function of q2. Therefore L is minimum if q2 is maximum, and the maximum value of q2 is equals to 1, and hence q1 equals to alpha to the power 1 by n. Thus the shortest expected length confidence interval for theta is given by x ordered n comma x ordered n by alpha to the power 1 by n. Here x ordered n denotes the observed value of x ordered n obtained from the sample. Now we consider our last example. Let x1, y1, x2, y2, xn, yn be n pairs of observations drawn from bivariate normal population with parameters mu1, mu2, sigma 1 squared, sigma 2 squared, rho. And we want to find the shortest length confidence interval for the parameter theta, which is equals to mu1 by mu2, which is the ratio of the means. Here mu2 is not equals to 0. Let us define zi. Zi equals to yi minus theta xi. It follows normal 0 comma sigma 2 square minus 2 theta rho plus theta squared sigma 1 square. The sample variance of zi is given by s squared theta is equals to 1 by n minus 1 summation over I from 1 to n zi minus z bar whole square, which is equals to s2 square minus 2 theta s12 plus theta square s1 square, where s1 and s2 denotes the sample variances, s1 square and s2 squares, and s12 denotes the sample covariance between xi and yi. Thus root n into z bar divided by s follows Tn minus 1, and it can be used as a pivotal quantity for setting confidence interval for theta. So we take q equals to root n z bar by s, and hence it is possible to find two quantities small q1 and small q2 such that probability under theta small q1 less than equals to capital Q less than equals to q2 is equals to 1 minus alpha. We know minus q1 equals to q2 equals to Tn minus 1 comma alpha by 2. Therefore by symmetry probability under theta n into z square theta by s square theta less than equals to t square n minus 1 comma alpha by 2 is equals to 1 minus alpha. Or probability under theta s2 square minus 2 theta s12 plus theta square s1 square less than equals to n into z bar square by t square n minus 1 comma alpha by 2 is equals to 1 minus alpha. Note that t square n minus 1 comma alpha by 2 into s2 square minus 2 theta s12 plus theta square s1 square equals to n into z bar square defines a parabola in theta. Depending on the roots of theta, the interval can be a finite interval, the complement of the finite interval of the whole real line. Let us close our discussion with the following remark. Like point estimation, the problem of interval estimation is twofold. First, there is a problem of finding interval estimators, and second, there is a problem of determining good or optimum interval estimators. In this lecture, we have discussed a method of finding a good confidence interval by minimizing the expected length of the interval. The other criteria of getting an optimum confidence interval will be discussed at the end of the lecture on testing of hypothesis. In this lecture, we have seen that the choice of the pivot plays a very important role in the interval estimation. A pivot is a quantity, it is a function of the random observations x1, x2, xn and the unknown parameter theta such that its distribution is independent of theta for all values of theta. In the examples, we have seen that the shortest length confidence interval can be obtained by using such a pivot.